Hello, good morning. هذا ولا لانك.
Yeah,
Yeah,
good morning,
morning,
Carlos.
Okay, all right, good. Lalike, carry on, please.
Okay, thanks, Odion. Good morning, Carlos. Thanks for joining us. The webinar will be starting at 11:30. So we'll just be on standby, or we'll wait for more people to join us, and then we'll start by 11:30. Thanks for joining on time. And good morning, everybody that has joined.
Àbámi, ẹ kú gbàdùn. Ẹ wá kíláàsì lé ní. Webinar kan ni. Optimization kìíní data analysis àti AI. Ọ̀pẹ̀ṣẹ́ iná ti Python.
this webinar. Okay, welcome to today's webinar. On behalf of the SP Lagos Section Chair, Ms. Michael Oyere, I would like to welcome you to today's webinar on a comprehensive framework for production optimization powered by data analytics and artificial intelligence, organized by the SP Lagos Section 61. My name is Olanike Adeoye. I'm the main facilitator of today's webinar, and here with me I have Odion, who is also the section administrator. Okay. Just before we start, just before we go into the main webinar itself, we'll be having a quick HSC session. So Odion, can you please go to the slide? So we know this is the time of COVID. COVID is everywhere, and we'll just encourage every one of us to keep safe. Let's keep safe. Let's wash our hands frequently. Particularly this period, the Delta variant is real and it's more dangerous than the previous ones. So let's continue to keep safe. Let's wash our hands regularly. Let's use an alcohol-based sanitizer, and let's wear a face mask when we are in the public and we can't really practice social distancing. Actually, practicing social distancing is the best thing to do. It actually helps a lot. Let's try and avoid large gatherings. But if we are feeling unwell, let's attempt to self-isolate and call the NCDC number as provided. Okay, thank you. So for today's webinar, we'll be providing insights on a comprehensive framework for production optimization, which will be covering topics on organization, instrumentation and control modeling, optimization, surveillance and execution. We'll be having a descriptive knowledge on how data science and engineering analytics can help in streamlining the business processes involved in optimization. You all agree with me that with the current economic climate, optimization in every sphere is very important. So we'll be having a case study of an approach that has worked well in practice for multiple fields in the North Sea and the Middle East. Please, let's pay attention. Let's eliminate all sources of distraction so that we can maximize value in today's webinar. And in order to keep decorum in the room, please, we kindly ask that you keep your microphones muted throughout this webinar. But please, we implore you to please type your questions and your comments in the chat room. So that way we'll be able to coordinate the questions and comments, and we'll be able to address everything that needed to be addressed in the interest of time, as we don't intend to keep you for long. So we have with us this morning a digital oil field specialist in Abu Dhabi National Oil Company, ADNOC's Subsurface Excellence Center. He has worked as a petroleum and a reservoir engineer for the past 15 years in multiple roles all over the world around reservoir management, well integrity, production optimization, and integrated asset modeling for Landmark, Maersk Oil, North Oil, and ADNOC. His special interests are in operational excellence and creating solutions to streamline the work process of engineers and integrating physics with data science. So please, let's make welcome with me this morning, Carlos Mata, for today's webinar. So Carlos, over to you.
Oh, yes, hi, thank you. Let me start my video here. Okay, and I will share my presentation. Share screen. Just bear with me here 1 second. Can you see my slides?
Yes, Carlos, I can see your slide.
Okay, great. So, I will be talking over the next 45 minutes about the topic that I'm very passionate about, which is production optimization with a digital twist. So, how we're applying the latest advances in digitalization for improving the optimization process, all the way from modeling to execution. So let's start with some disclaimer. I am in no way representing ADNOC here, so I come here as Carlos, not as ADNOC. And about the reproduction of this of the video and the presentation itself is with permission from SPE and myself. Okay, so the agenda. So first, plan to go through the business building blocks of production optimization and the value drivers. And then we go into each one of the elements and those building blocks, which are organization, instrumentation and control, the production data itself, modeling, optimization, surveillance, then execution, and then how we can go about digitalizing the process. So let's start with the value. So for digital projects related to optimization, efficiency, and recovery factor increase, different companies have different perceptions, but overall, the value of production optimization and operational efficiency, so two very interlinked concepts, is pretty large. So you can see that it's around 5 to 10% for some companies. Let's say that 5% of production potential gain is the size of the price. Very significant, considering that this is a very low cost barrels. It's the cheapest barrels you can get. All right. So what are the components of this value? How do we get to this 5% price? Well, it all starts with the organization. So those of you coming from Shell, you hear all about this people, process, technology. Well, let's start with the people and process, making sure that you have the streamlined workflows, the right KPIs, procedures, and guidelines. This is always the base and the most important thing to get to properly gain the value. Then you need the technology. So it all starts with being able to measure the wells and being able to control them. So instrumentation and control. So once you have your measurements, then you can have proper models. So then you get into integrated asset modeling, modeling your well and your production network facilities were required, etc. So you can then calculate different optimization scenarios. But that's not enough. You need to be able to execute them. You need to be able to know what each well is doing at any given time. So you can effectively know if you can do something or not, right? So that is operational excellence, being on top of everything. So it enables the execution of your optimization scenario. And the last one is analytics, right? So once you have all these building blocks in place, all the data that comes out, you analyze and you gain some insights. And that's the cherry on the pie. Right? So that's not the big game changer. The big game changer is getting everything working together as a well-oiled machine. Right? So the value drivers for digital projects, let's say we work on the integrated asset modeling, situational awareness systems with a price of 5% potential upside. And in parallel, we work on trying to increase our recovery through a better reservoir management. So different value drivers, production optimization, operational efficiency. And we see here, what is the value realization? Well, 1% recovery factor increase. This is from reservoir management improvement, usual number that is stated. Then for operational excellence and production optimization, 5% potential upside. This is impossible to achieve without digitalization, without measurements, without models, not possible to achieve. And so you need to have everything in place. And also as situational awareness improves, then you can effectively compete with the drilling to a degree, right? So you lower your drilling cushion because you're able to get some additional potential by just operating the wells better, right? So that's not going to last forever, but it does help, and it does bring a lot of value at low cost by converting the locked-in potential to available potential in an effective manner, right? So what are the elements in the production optimization? Let's make a graph that illustrates all these different elements there. So let's start with organization. So oil companies have a reservoir department and they have an operations department. So the first question is, where does our guy sit? The surveillance and the optimization engineer. Well, we've seen they can sit in any of these two. Some companies and some business, some countries, they In some areas, they prefer to have them in the reservoir department. Others prefer to have in the operations department. Each one have a different KPI, so it's a very important. The first important decision is where do we put this person, which sits at the intersect between reservoir and the surface operations. Right? There's no right or wrong answer in this case. So it's just about setting the right KPIs, the right framework for this person to be as productive as possible. Then you have an integrated operations center, which is always recommended, which is a very lean team of few people that are the ones that are directly in contact with the operations in the field, right? So you may have process engineers, planner, logistic coordinators, production programmer, and one petroleum engineer, right? So this petroleum engineer is not the person that creates the models or designs the wells. Those are here, all right? So this is the person that does the day-to-day optimization. And this is the person that supports that and gets the models. And they all work with the models, right? So different tools. What are the different tools to get to this process working properly? Well, one of the key tools is to have a proper opportunity register. This is also called the hopper of opportunities. So how do you capture all the ideas for increase of potential so they get properly matured and executed? A digital oil field solution for managing your integrated asset models, keeping the models up to date, potentials and shortfall monitoring and tracking, short-term planning tools, surveillance by exception, super important, and then high-level operational activity tracking. So how do you know that each person is doing the right thing at the right time with the right context, right? So there's a lot of room for digital improvements in the process. So let's start by the first one, the organization. So always a good idea to map your business process, right? So all the key business processes should be mapped as they actually occur. And this drawing here shows an example of a business process related to instrumentation, for example, right? So focusing on processes that have very tight deadlines and create stress in the organization, frequent processes that are very work intensive, processes that have a biggest financial impact, and the processes are suffering from a large backlog currently, right? So this activity is bread and butter for companies like McKinsey, BCG. Typically, you hire them for this, optimizing your organization. It's rarely done internally, but this is a very, very useful activity, and it's not so complicated to do. So let's put some example of cutting waste. Let's put one example here. Several wells remain dead for weeks, but they're still reporting if they're producing. Common, very common. Then you start finding the clues. So the clue can be, okay, well, these wells, they have integrity issue. That's a pattern there. So what's going on? What's the root cause? Well, it turns out that there is no clear procedure for the operator. So the operator, they see that, okay, you're not allowed to put artificial lift, but you are allowed to produce a well. So they just open the choke and hope the well will flow. Well, probably not the safest procedure. So the solution is to add a standard procedure to close the wells that cannot flow naturally, right? So this is just one example, and it could be others, like metering problems can take years to solve, and it may end up being some issue with the SAP or whatever ERP platform you use. So always important to see if these platforms are creating a bottleneck in the process and see how it can be improved. Or jewelry equipment in the wells, the downhole gauges are not lasting. Start digging and digging and digging, and then you may find that there's some problem at the rig side of something that is consistently being done wrong, right? So then you apply, and then you find the issue and you try to correct. And there's several techniques for doing that. So process excellence, Six Sigma, Lean, day in the life of. Important not to overcomplicate and just focus on the biggest value there. So this is an example of what can happen as a result of this exercise, right? So you may model the process. This drawing here is an opportunity management process, generic, not oil and gas, but the pretty generic opportunity management. You come up with an idea, that idea, you need to put some value, that needs to be approved, and then you request more information, and then you execute and then get the value, okay? So once you model the process, there's digital platforms like Visagi, Microsoft Power Automate that allow you to go from this drawing to this system here, where you can automate. And it even comes with the web interfaces so that different people in the organization can interact and can work out the process. Right? So you don't need SAP for everything. You can build your own workflows, especially stuff that is day-to-day business critical. You know that you want to make sure that you are optimizing it and making it as safe as possible, right? So a lot of trial and error is always involved in this process. Therefore, these tools become very, very useful. A lot of use cases for opportunity register, operational activity tracking and management, well and pattern reviews, managing tickets from multiple automated systems, etc. Right? So you automate your process, and then you have a lot of different analytics that you can have on top of that process, thanks to this type of platform. Right? It's accessible. Many companies have it. Many companies have the Microsoft tools now that come with a lot of these great tools. So just speak with your IT departments and see what you can use. Right. So the next step. Now we go to technology, instrumentation, and control. Right. So new fields in general, they come already by design with instrumentation and control capability. But how about the old fields? So retrofitting instrumentation in legacy wells. Right, we are in year 2021. We are in the future right now. So there's no excuse to have dumb wells anymore. So wells, they need to be instrumented. Engineers need to be able to see the parameters of the well in real time in the office. Yes, but that's expensive. Well, not anymore. So you have a technology like low frequency radio transmission, like LoRa. It operates on battery, has a wide range, 8-kilometer range. They cost $1,000 per transmitter. Minimum footprint is just 1 meter. No need for cable, solar panels, or anything. And you can mix it with other technology like WiMAX, wireless HART. There's a lot of different developments in this area. So this is one example in an offshore application where you have a lot of antennas, transmitters with antenna with a 500-meter range, and then one big antenna operated with battery, right? So you change the battery every once in a while. For this one here, every 2 years, and this one every 10 years. And that's it. You instrument your whole field. So you do that thousands of times, and then you get a big field fully instrumented. And then these instruments, they tell you not only the measurement, but also how much battery they have. So you can plan in advance when to change it, right? So this is kind of the paradigm here. The traditional way is to go SCADA, control system, enterprise historian, all the way to the engineer's computer. That's okay. That's always what we want. But in many cases, this is prohibitively expensive. So you can always go the industrial IoT device way, right? That can write directly to the cloud or on-premise historian, and then all the way to the engineer's computer. And it looks like this. It's just like this. You install it very quickly, do your risk assessment, metallurgy, etc. Everything matches, put it there. You get your signal, you get your numbers, you get your value. Right, so once you get your numbers, how do we make sure that those numbers get to your desktop so you can actually get the value from it? So, well, the data follows a tortuous path. So it goes all the way from instrumentation and the actuators that transmit the data through a remote terminal unit to the control system. And then from the control system, you have the historian, which brings the data to the office, right? So it collects the data, it aggregates, it organizes, and then that data goes into systems that are automated or manual, right? For the engineers and the general users to use. So as you see many elements in here, there's also many bottlenecks, right? So this is a limit diagram for the data bottlenecks. Just like production and oil, you can also have bottlenecks in data. You can have problems in the transmitter, problem in telemetry, or simply the measurement is not being stored, or the measurement is there, but it's not being used, right? So we always need to get this bar, the green bar at the end, as high as possible. So you use 100% of all the physics measurements that are happening in the field. There's a reason why they were put there in the first place. So figure out what is the reason and use it. Pretty boring, but very important. Right, so now we get into the most fun part, which is modeling. So about production system modeling. So in general, just like reservoir engineer have the dynamic model, the geoscientists have the static model, the surveillance and optimization engineer have the well and production network models. So this is one example here. But it all depends. It all depends on what is your objective function, right? So if you're trying to just increase, maximize the production in a field, oil, for example, then it's okay with the well and network model. But there's some more complex cases. Let's say that you have a more mature field that has a lot of constraints on water. And then, well, there's options. There's complicated and there's more simple options, right? So in this particular example here is that we have a model, the gap model, but then we add a lot of linear elements in the middle that try to capture the flow of water in the facilities, right? So that we can then optimize based on that, right? And forecast. And then there's the other option where we don't linearize anything. We just go full physics. And this is an example where for a gas asset where we produce gas, inject gas, it's a gas condensate. So we model the process facility, so we maximize the condensate production. But we need to integrate everything together into a single system. More complicated, but we need to do it because that's our objective, to optimize this process, right? So always picking the simplest models that describe the process we're trying to optimize, right? So if you can model it simple, just go ahead and do it simple, because otherwise it becomes a headache. Headaches are only worth it whenever it pays. Okay, so again, the more complicated approach, full physics, process, simple approaches for facilities. Let's say, you can model your entire facilities here. You have all the different elements of the facilities, the main elements of the water treatment, etc. You can model it here, and then through the magic of linear programming, it becomes a matrix. And that matrix you solve, and it can optimize the whole thing. All right, so then you figure out how to mix it with the full hydraulics, okay? Which I'm going to show an example later. So as you see, the models, they're not only of one type, always need some combination for you to achieve your objective. So talking about that, so we have discussed about physics models. So just like we use these physics models, nodal analysis, etc., we also use the data-driven models. So the difference between the physics models and the data-driven model meaning being derived from data, right? Is that the data-driven models are very good as descriptive models, right? They can describe what the well is doing today. But the physics models, they tell you what the well should be doing today. So that is the key difference between them. Can you ever replace physics? No, never. Don't attempt that. So it's about how do we supplement that with more models that are independent from your base models, so you can get a better picture of what's going on, as long as you keep it simple, right? So always important to keep it simple. Adding more bells and whistles where it's not required only makes it worse. There is an optimum, which is around here, an optimum model complexity. That applies not only to machine learning, data science domain, for those of you that are delving into that area, but also to the base physics workflow. Right, so yes. So then we have a ensemble machine learning models. So sorry, I'm hearing some noise here, but that's coming from my side. Also, a second. Okay. So how do we apply machine learning in the production domain? So well, this is the use case. One of the use cases. So you have a well. So the well, you test the well sporadically, but you measure pressures and temperatures in real time. So how do you move from pressure and temperature to rate, so you know how much the well is producing in between the flow test? Well, first you need to identify where are the measurement points. So if you have a downhole gauge, you have a measure here. If you have more gauges across the choke and the flow line and manifold, then you have different points of measurement. So every element of the production system that is in between two measurement points of pressure and temperature, you can treat it in isolation. It's a control volume, right? So, and for each one of these control volumes, you can have multiple algorithms. And for each one of those algorithms, you can have multiple models. So that is the concept. Making a single regression model from data, you will notice that it tends to be a very crappy model, or in any case, overfitted. So how do you tackle that? Well, you do something called ensemble. You stack together many different crappy models so that the final model that is a combination of those is actually pretty good, right? So you try to find as many uncorrelated estimates of the same value as possible and combine them all together. So at the end, you get something like this. You have a test here, but you want to know what's happening in between. Well, you get your estimate, and then boom, you see the well, it died. So you pick it up using your fully data-driven model. It runs incredibly fast. No need for Prosper. You do need Prosper, but probably this is good enough in many cases, so you can then jump into Prosper to try to find out what's going on. Okay, so how you train it? Well, you split the data into many different buckets depending on how much data you have, and you leave some data at the end for validating. And as I mentioned, you split by control volume, then you split by algorithm, and then you combine the whole thing together, right? So one well can have 25 models, but you can reduce that to only 3 models, one for each control volume, and then you combine them all into one single model. That single model is going to be pretty good. So this is an example here of a well. You have the flow line. Based on the pressure drop in the flow line, you know how much the well is flowing, and this is the model result, and this is the error bands. And then the choke pressure drop, you can also estimate how much is the flow. So you see how each model is different from each other. And then you combine the whole thing together. And then you see a better representation of what the well is doing, but also a better representation of what is the uncertainty on your estimate. All right, so you can check this SP paper here for more information on this one here. So that's data-driven models that you create from data. So, but then you can also do a trick. You don't need to have the nodal analysis software for everything. You can also fit a neural network from the nodal analysis, right? So you can create a gap model, a small one like this one here, run it 5,000 times with multiple combinations of inputs and outputs, and then you fit a model here. This, for some people, it may look hard, but it's actually 4 lines of code in Python. Okay, so go ahead and try it out. And then you have also simple physics. So the equation of the through a restriction to model the flow through a choke in water, or you use the Thornhill-Cravier to model the choke, the flow through a restriction. But this has some more complication because of the set factor. So probably better for the neural network in this case. And then you have, if you have a pipe that has a measurement upstream and downstream, can be a tubing, it can be a flow line. Then you can apply what you learn in university, the fluid in pipes, and just solve it. And that's your virtual meter there. Right, so these are some examples. So this is a offshore field, large offshore field with 13 different platforms with facilities. And of course, I hit all the numbers, but you can see more or less the trend here. So you can see that the full field, which is the graph on top, you can see how progressively the models are improving and the error is reducing. So at the end of the day, we have less than 2% error compared to the model. So between the actual measurement of the output of the field and the models. That's easy to achieve in relative terms for a big field because of the magic of the law of big numbers. As you get into more and more detail, it's more difficult to get a good result. So for example, let's get this platform here. You see how it's all matching well? Well, I wouldn't bother about this one. Everything is working fine. But you see this one here on the right, the models are just not matching at all. So I would focus on these ones here. And that's how you go about these models. focusing on where the value is in this case. So you have multiple redundant meters across the field. You compare it against multiple different estimates using your models. And then you can get into conditions, tools like this that allow you to go directly to where the problems are. For validation of measurement, you can use those proxy models. For example, you can estimate water injection rate in real time based on the choke pressure drop. So you'll be surprised that more than 10% of your single phase flow estimates are completely off. That's very common. Completely off, meaning like the well is injecting less than half or 5 times more than what you think it is. But if you run a virtual meter and you compare it against your measurement and you see that the values are on top of each other, then you wouldn't bother. This well is okay. And then you see the same thing for gas lift. You see this well here, you see this very large fluctuation on the measurements of gas lift and your proxy model, how they differ. Well, this deserves an investigation. So in this particular case, they investigated and they found some problem in the flow computer, fixed, problem solved, the measurement is okay, you trust it, you don't get confused with your other stuff, right? So that's the value in there. So monitoring your production potential, and if you're using it effectively, monitoring your measurement. You don't just trust your measurements blindly, you also try to validate them in real time. So surveillance. So now we get into a more fun part. So okay, so now you have your models and you're able to run your models in real time. So what's the most effective way to use all those models that are now running in real time? Because you may have 3 engineers and you may have 5,000 measurements every 20 seconds, right? So just impossible to go through every single well every single day. But we want something better than that. We want to go through every well every 15 minutes or every 10 minutes. We want to know what every well is doing every 10 minutes. So the only way to do it is with automation, right? So let's say a field we have that where we have 5,000 measurements and let's say 400 wells. We want to convert that into 100 activities, 100 tickets. So conversion from here to here, you do with surveillance by exception and using an expert system. So basically, we have a catalog of different types of diagnoses and recommendations for each one of those diagnoses. Let's say the system detects the well is dead, and it tells you why it thinks the well is dead and what is the recommendation. And it creates a ticket, and that ticket is assigned to someone. And then those people, they forward that ticket around until the problem is solved. Boom, you get the value, right? So it's not only getting the models, it's not only doing the automation of the surveillance, but it's also managing the actual business process to execute the whole value chain. So this is an example of a tool that we created in ADNOC, and also similar things are in place in several places. And this one is combining your measurements with your virtual meters, which can be machine learning models, like these two here are machine learning models. Say you have, for example, machine learning, these two, proxy neural network model, spline curve, full nodal analysis, production data, and real-time instrument data. Combine the whole thing together, the system automatically identifies problems, SAP A, SAP B, dead, bullheading gas lift, slugging, hydrates. So you click on it, it gets it created the ticket for you, and then you just forward to whoever you think will fix it. And they bounce back and forth until the problem is solved and the value is achieved. That is the concept, more or less. Right? So how is this achieved? Well, you can do rules, a rule-based system. They say if the let's say a water injector, if the rate goes up and the pressure goes down and you didn't change anything, you would worry that that injection induced fracture, for example. So that creates a ticket. This is a simple rule-based thing. Then data is not so clean. So there's other technologies that you can also use to assist that, like Bayesian networks. So this is a old school AI tool, and old school is good. It works, it's explainable. You define your cause and effect, and then you let the system give you the probability of what the problem that is happening there. So that is the concept, right? So through a series of rules, you discretize your measurements, which are continuous numbers, into flags, like, oh, my pressure is going up, down, etc. You do that for all the measurements. You combine them all into one logical structure, and then that thing will spit out what is the probability. You are 60% likely that the well is having a hydrate problem, for example, right? So that's more or less the idea. And then if you're missing some data, if you lose one pressure tag, well, then it's not 60%, it's only 40% sure. That is the idea through the power of these probabilistic models. So that's the AI component. No deep learning in this case. We tried, we failed. You need way too many samples. Better to you define the structure of your algorithm, of your logic of the thing. Okay, so now go for optimization. I hope you're still with me there. So this is the fun part. So computing the potential so that then you can later execute. So how do we get to a position where everyone gets their share of the locked-in potential? So many of you are familiar with this type of potential breakdown, especially those that I learned this in Total with the Total guys. My former boss is in here. I can see his name. So I learned this from him. So the potential breakdown, very important, right? So you compute the potential all the way from reservoir to the wellhead, to the production network, to the facilities, through the export, and then including a lot of different reservoir management guidelines, and then what you actually commit to and deliver. Okay, so each one of these losses here, this locked-in potential, you can map it. And depending on what is the reason why the well is not able to perform to its potential, you have a responsible. So each person is mapped to a different type of thing, like low productivity, shareholder guidelines. That's a different thing. Reservoir management guidelines. Well integrity. Close for well integrity is for the well integrity people. Everyone gets their share of the locked-in potential. The well is not producing because we're waiting for engineering to hook up the well. Okay, engineering, you have 10,000 barrels of oil per day waiting for you. And you count the time and you multiply by the value. Right, so facilities, bottlenecks and in the pipeline and flow line, mechanical problems in general of the surface network, liquid handling capacity, water handling capacity, etc. And then, so once you know how much is your technical rate of your field, then you apply the OPEC quota, for example, or these VRR constraints, the voidage, etc. So then you can commit to certain production, and then you monitor what you actually deliver, right? So on plant on time, etc., etc. So all this distribution, all this breakdown, it can be automated. It should be automated. It's very important to get a streamlined workflow for that. So, but as you can see, it involves not only production, but also reservoir management. And including reservoir management is, and every other constraint is not trivial, but very important. And every field has its own nuances. So optimizing, you need to consider not only your production network, but also your injection network, ugly drawing this one here, and your interwell connectivity. So how much of each injector is going to each producer, so that if you're not injecting in one area, probably you shouldn't be producing for that area, or at least put some heavier weight on those wells so it makes it less likely to produce, etc. And your hydraulic models, right? So describing the whole topology of your production and injection system, all the way through the reservoir and the production network, and then embedding the hydraulics, right? So once you combine all that, then you can do several optimization schemes, right? So as I mentioned, optimization is not just the hydraulic, right? So this example here shows the different sectors, because each different sector of the reservoir may have a different target, etc., that you want to achieve. You have constraints of the facilities. You need to monitor that. And you have even the OPEC quota, etc. So every field, every well is different, have their own personality. Then you have individual well KPIs there. So and you see, if it makes sense or not based on the voidage replacement for that particular pattern, etc. Right. So many ways to do it. So so you see that the objective function is up to you to define. But it needs to be an objective function that captures the, I got it wrong here, production optimization and the reservoir management, right? So you can say, okay, well, I want to maximize my profit today, but I want to minimize my deviations for my voidage target. Fine, that's one way. Or you can go it super simple, saying that, okay, it's the sum of my profit divided by the reservoir pressure. Meaning, if you have low reservoir pressure, you make it, if you have a low reservoir pressure, you make it harder for it to open the well. All right. So many different ways to do it. But at the end of the day, this is kind of a trial and error process until you get to your solution. So the process involves running your hydraulics to compute the potential, then you feed it through all your reservoir constraints, and then you back to the hydraulics to validate, to make sure that you can effectively achieve it until the reservoir engineer is okay with that setting. Right, so and then the same principle, more or less, should also apply not only for the instantaneous optimization, but also for the forecast. Okay, so this is one example of something that was a lot of fun to do, which is, okay, how do you optimize the forecast of the field? How can we find opportunities that for stuff that will be a problem in the future, but it's not a problem today? Because there's a lag. It takes time to do stuff. So if we can discover a problem that will happen 1 year from now, then and it takes 1 year to prepare for it, to solve it, then then you need to do the short-term forecast. Okay, so you have a simple reservoir description here, a material balance or decline curve, which is good for short time frames. Hydraulic model, linear model if you need, and then orchestration. Right. So this is an example. So this field, new guideline from the government: 0 water overboard. Not allowed to do overboard. So starting from January 2020. So we measure what is the impact of that. Well, the impact is a lot, right? So it will cost us 5,000 barrels per day. So when digging through all this impact, that we calculate here, we see, okay, where is my bottleneck in all this complicated process? It turned out to be the flow line of the disposal well. One of the 10 disposal wells that are scattered all across the field, one flow line was going to cost us 5,000 barrels per day 1 year from now. So you have probably time to work on that because there's a schedule to drill another well, but they didn't think about the flow line, that flow line. So that's added in the schedule. You get your NIDA. You make your money. All right. So that's more or less the idea. So you may have heard a lot about another buzzword, digital twins. So and digital twin is basically embedding models in your day-to-day. So you start with your digital model, which is just the usual network model, for example, where you try to reproduce your physical entity, and it's all lagged. You update it every once in a while. A shadow means that you update the model continuously, but you don't use it continuously, and you don't feed back on it. The model doesn't feed back into the production system continuously. And then your famous digital twin word that everyone is talking about now, and it's feedback, establishing the feedback loop. So it's all about creating feedback loops. How do you make sure your models are giving a feedback to your operations in a timely fashion? Right. So, example, model gap, fine, but if you don't keep it up to date, then it's useless. Then you have an orchestrator. Let's say IFM, IVM, any of these tools, OVS, etc. So you keep this stuff updated. That's okay, but you're not using to execute, right? So there you go, execution. So you go all the way from your model to make sure your models are running continuously and continuously updated so you can then execute. So that's what I would call the digital twin in the production domain. You need all these different moving parts together, everything working together. So I realize I'm running out of time, so probably 5 more minutes, if that's okay. Okay, so silos are okay, as long as the handshake is okay, right? We're doing a word salad here, but it's okay. You know, you don't want to put a petrophysicist next to a rotating equipment engineer. They have nothing to do with each other, right? So that's what I mean by silo. That's fine. It is the handshake. What is the output from one team to the other team, and how is it used, and how is it fed back? What really matters, right? So so then in the digital spectrum, you have your reservoir engineer that does the reservoir management activities. They provide the constraints for the petroleum engineer to run their optimization. And then there could be another platform. There needs to be some bridge between the petroleum engineer and the disciplines involved in operations, which are well services, maintenance, production operations support in general, right? So you can tackle each one of these different workflows, right? So ultimately, once you make sure that you're on top of everything all the time, then you can achieve the dream, which is to optimize closed loop. The dream. Let's tackle each one of these elements first. All these black arrows here are essential areas to focus. Right, so enforcing the feedback loop. So this is the concept of merging the surveillance by exception with the action tracking, activity tracking, assigning responsibility for executing and activities to gain value. Right, so you get the field, it goes to an automated system that automatically diagnoses the wells. It fits the funnel, the hopper of activities. The petroleum engineer then is the first person that validates. They're the well owners in this case. So they validate and they say, okay, who is responsible to fix this one? So then checks it against their counterparts, the reservoir engineer, production, process engineer, production, etc. Then that gets routed to the executors, well service, maintenance, etc. Right? Your organization may be different, but in general, the principle is the same. Is how do you enforce this feedback loop? So it goes this way, then this person says it's done, check it back again, and then it's like, okay, I see some issue here, please reservoir engineer help me out, bounce it back, and that's all, one ticket. Once it gets solved, you can track what everyone is doing. You can see at any given moment in time who is responsible for what, and when there is supposed to get it done, and what is the locked in potential associated with that activity, right? So automated systems allow you to then keep track of that. So you can see over time how the value is growing and how you're actually achieving that. Where are the bottlenecks? Where are the backlogs? Who is doing what, when, and how? So not only useful for managers, it's also useful for people to know where their activity is stuck at. Fixing the meter, the flow transmitter. Okay, well, this person is working on it and they wrote this. Boom. So, and since everything is recorded, everything, it's a knowledge base that you start building, right? So the last slide is digitalization, right? So we go with this buy versus build dilemma. In our case, we a lot of the solutions there you need a vendor to do. Others you can do yourself, right? So how do you decide what to do yourself? Well, this is an assessment that needs to be done, and it depends on several matrices. So you can search, you can use the matrix that I put here on this slide, or any other, but it depends on the buy-in from the management, the level of expertise. If it's something that it requires you to create a new simulation engine, forget it, buy it. just get a vendor. If it's something that is a combination of many small, simple things that need to be orchestrated together, probably you can do in-house because you can probably, using commercial solutions, make it scalable. Example, data, sources. This is a foundation. Then there's around 5 different software elements that if your IT department gives you, you can do miracle. So first, access to open source libraries, Python, R. Then the data pipeline, feeding all these databases through a single interface, right? Foundation. Then a workflow automation platform for business process, like Visagi, Microsoft Power Automate, for example. Then a workflow automation platform, so you can, let's say, run models in real time, continuously, of any type. And a business intelligence platform, Spotfire, Power BI, all these tools. If you're still using Excel, please complain to your departments. You need to start using Spotfire or Power BI or the other type of tools of that nature. So you get all these different elements together, you can build many things. So that's more or less the approach that we use to build, for example, these solutions that you see here, right? In-house. Other, buy, right? So putting it all together, this is the final slide. In terms of the creaming curve of value for optimization, you have organization, focusing on the modeling the business process, cutting waste, and automating the process. Instrumentation and control, just go ahead and instrument them. Is very cheap, no excuse anymore. And consider, advancing, using more advanced controlling, more model fields if you can. Then modeling, every well, every field needs to have an up-to-date model. So you need also not only the model itself, but also the tools that allow you to keep that model up to date, model live, right? Embedding reservoir management in the process. Surveillance and execution is surveillance by exception, and this ticketing system, right? The collaborative system that we just showed, right? So those are the elements. Yeah, I realized I probably went like a machine gun here, but I'm available for questions. Just throw any questions you like. I have all the time in the world to answer them. Thank you very much.
Excellent. Thank you very much, Carlos, for such a mind-blowing webinar presentation. You really went at the speed of light, I must confess. A lot of new things there. I like one of your last comments saying that if you're still using Microsoft Excel, we should complain to our management because we should be using Power BI. I couldn't just stop but laughing over here. And indeed, that is the truth. And you've really learned so much that while we rely on physics models, which is telling us on what the field should be doing today, but the data-driven model is actually what is telling you what the field is actually doing today, because that is your real data that you have. Also, you've taught us about the value drivers, the recovery factor increase, operational excellence, and production optimization, which is what should be keeping the business alive, and also helping us to look into the future, where you've actually said we are in the future already. So that is really very, very, very interesting. And also, it's impossible for us to reach the field potential without digitalization. So if we're still living in the old world where there's no digitalization, everything is analog, then we can't reach the potential. Thank you very much for that. I wouldn't be able to go through all. You've gone through a lot in the short time, and we have a couple of questions that are trooping in. So I'd just like to ask the questions as they've been asked. So we have from the first one from Evan Zapata. Carlos, nice presentation. Have you managed to make these digital twins work seamlessly for your engineers from A to Z, and how were you able to achieve that? If you can please answer that, Carlos.
Yes. Yeah, for example, there's different levels of complexity, and it always depends on the type of field that you are and the type of KPIs that you have. I would say that there's one example that we had in my previous job is that you need a hook. You need something that cements the workflow, that makes sure that you keep everything up to date, and then the optimization, it's a kind of a side benefit of that. Let me explain myself. You can have a monthly workflow where you have to describe all the potential breakdown of the field and say that, okay, where are the barrels? And you need to know exactly where are the barrels, because that gets reported all the way up to the management chain. Uh, it's a tedious workflow, but it's extremely valuable because as a side benefit of that, you have up-to-date models and you are actually on top of your wells, right? So having a hook, it's what makes the whole thing work, right? So a hook that ensures that kind of a certain level of compliance. And the same thing for the short-term production forecast. You can say short-term production forecast, use the hydraulic model. That would add a lot of complexity, but as a side benefit of having to use the hydraulic model for doing the short-term production forecast, you will end up having very nice up-to-date models that you can use for optimization, right? So yes. So the A to Z. Well, we've had I would say that we've had that. It is the tricky thing is how do you keep the people engaged? So and it's not easy. Let's say you make a solution, right? Let's say this ticketing system that I talk about. You can make this very well made, and having all this escalation to management, etc., and the timing, and etc. And then the first thing that people will say, like, I hate this. This is horrible. I don't have room to play with or creativity. So they'll just ditch it. So there's a very thin line in the process automation. You need to keep it flexible and as simple as possible. Otherwise, the thing will just die. There's the thin spark and flame of creativity needs to be kept lit by keeping the things simple, right?
Yeah.
So that's kind of the trick of it. Yeah.
Thank you very much, Carlos, for that. Thank you for that explanation. The next question is actually coming from Oluwafemi Olominu. Said, thank you for the wonderful presentation. So in your experience, what fraction of the typical skills and knowledge of an optimization engineer falls into subsurface engineering, process engineering, and data analytics? So what will be the most effective skills composition for a data-driven optimization engineer? And I think if I latch onto that question as well, knowing that in our universities, as a petroleum engineer, you never get to be taught anything related to data-driven approaches that we're talking about, traditionally. So just wanted to add that to the question. Okay, over to you, Carlos.
Yeah, this is a very interesting one. It's a question that I get asked a lot. And a lot of people ask me, like, hey, I found this Coursera course from IBM or whatever. This is the most, there's many. From this university, from Stanford, from MIT, that is great if you're a mathematician or you're a practitioner. So use YouTube, use GitHub. There is a lot of people that are putting their content specific for oil and gas and all their code in GitHub and in YouTube. I can share with you some of these people, the groups that are doing that, so you can get a head start in there. Because if you do a generic training on this machine learning, data science, AI, by the time you get to you move from neural network to support vector regression, you already forgot the neural network because you don't have really the use case in your day-to-day work, right? So best approach is copy the code of other people. find what other people made and just copy it and use it for your own. And people are very generous lately and putting a lot of code online. So just go ahead and pick it up. So check out the Norway Equinor. They put a lot of data for a field called Volve. And there's a lot of people in industry that are playing with that data and creating many nice things and data-driven workflows and solutions on top of that data. So you can see their code and you can share and you can talk with them. That is the best way to learn by far. And in terms of the skills for the production optimization per se, best skill is get yourself into the collaborative environment. Try to find rotation there or something. Sitting next to the process engineer every once in a while is extremely useful because that's your counterpart on the facility side, right? So you're the well person, they're the facility people, and they know the full context of the facilities, you know the full context of the well, and you work together to optimize the whole thing. Yeah, a lot of engineers don't use PNIDs. For example, everyone needs to have access to piping and instrumentation diagrams. If in your organization you don't have access to the piping and instrumentation diagram, which is the tool of the production of the process engineer, that's telling me that that you're not working together enough, right? So need to work more together, and then you uncover a lot of value from there.
Okay. Thank you very much, Carlos, for that. Thanks for the response. So another question from David Cromwell. Amazing presentation. So how do you diagnose an automated system to detect when the tech goes wrong or malfunctions? And how can the system be maintained simple in such a way that issues can be diagnosed and located on time?
Yeah, so it's organic. It's continuously growing and evolving. So you start simple and you start with rule base. And then you put some rules in place that for the system to automatically detect a problem. And then that creates a ticket. The ticket can get approved or rejected. So if a ticket gets rejected, you have your statistic there, right? If a ticket gets ignored and it expires, you have also your statistic there. So after 6 months, you'll have a lot of numbers that are telling you what is working and what is not working. So then you can adjust your system and also, feeding direct feedback with the people. So it works better, right? You may find that you created some very fancy problem detection that detects a problem that almost never happens. Okay, probably you don't need that. Unless it's some heavy safety thing, right? So it's a trial and error process.
Okay, thank you very much for that. So again, from Evren Zapata, is any experiment changing the objective function of your optimization algorithms from production to emissions while still maintaining the value of the assets?
Oh, that's a super interesting one. Yeah, because in the slide we put, okay, merging production optimization with the reservoir management in the same objective function. I think the same approach can be used for emissions, especially if you can linearize it, which allows you to make sure that you get the single best solution. I believe you can use the same approach. Like, for example, the example that we put there where we linearize all the flow of liquid in the facility because there's pumps, so you don't care about pressure drops anymore because the pumps take care of that. So you linearize the whole thing. Probably you can also do the same or something similar for the CO2 and and the methane. But also in the modeling software like GAP, there's general elements where you can actually program logic inside that allows you to keep a better track of these elements there. So I haven't worked directly with the emissions, but I see that a lot of people is working on that right now. Yeah,
Okay.
it's a problem that is becoming more and more common. I'm pretty sure I'm gonna face that soon, also.
Okay. Thanks very much for that. The next question is from Ms. Michael Oyere. Excellent presentation, Carlos, and really mind-opening. So I really like he really likes the build versus buy analysis slide. So his question is, from your experience, how would you assess the reception of this technology by industry organizations, and what is the typical lead time to delivery? Is it 12 months, 24 months, or even longer?
Yeah, let's say it depends on where your organization is today. Like, for example, in my organization, where I'm working now, like we had, we started, the process took 1.5 years. And it could have taken less than 1 year, but the problem is that some of the building blocks were not in place. Like different IT domains, and not everyone had access to the Spotfire. So we had to start solving all these things, and that takes a lot of time. But then once it's there, it works. But it takes a lot of time doing that. And like, for example, 2 years ago, you said Python, and that was like forbidden. It's like Python, and people would just yell at you. Uh, a lot of stuff changed over the last year. Now, last year you said Python, and people say, like, "Oh yeah, we're looking into that. It's really nice. You know, we're doing something for you." So, now we got Python and R, which are super powerful tools, key enablers. So it took time. So then it depends on your case, and depends on the complexity. But you can have something, you can spin off something if you have the right tools in a month. Depends on the complexity of what you are trying to achieve.
Excellent. Thank you. Thanks, Carlos. The next question, lots of questions here, from Alexander Nwankama. Thanks, Carlos. A very informative presentation. So how do you correct for overfitting before you ensemble models during a real-time workflow analysis? So how do you correct for overfitting?
Yeah, so we grab the models, and I think I have I need to see, okay, let me try to, out of luck, no, I didn't get it here. Yeah, so here. So the machine learning models, you always need to leave a fraction of the data for the bland test. And then to reduce overfitting, you can use the k-fold cross-validation. And that is basically randomly segmenting your data set into different groups and training models for each one of those groups, and then combining them together. So that's why I say that for each algorithm on each control volume, you have 5 models. So you have, for the tubing control volume, the random forest model, you have 1, 2, 3, 4, 5 models. And you combine them together. Imagine you can have, for a well, you can have 30 different models that you combine them all together. So that is an approach that reduces the issues with the potential overfitting. And of course, you evaluate all the statistics for each one of those models, and then use your blind test data at the end, the data that you didn't use for your models. It's not polluted by the models. You run your models on that data and see if it works. So you run the models and you compare against that data, and then you see how well is performing, right? So the trick of the machine learning is to do many different independent models and combine them all together. A lot of crappy little models combined together end up being something really good.
Excellent, excellent. Thanks. I think I have one or two more, and then we'll round up. Thank you very much, Carlos. Okay, before I go to the other questions, I'd just like to inform our audience that please don't rush off. Would like to crave your indulgence to at the end of this webinar to take some snapshots of the webinar with the attendees, turning on their videos. Please, would like to take some snapshots so that we can see all your beautiful faces that participated in today's webinar. Thank you very much. Okay, so Carlos, so the next question actually is from Fraser Robertson. And it said, do you see a permanent role for a data scientist in the collaborative environment?
Oh, that's an interesting one. Uh, well, I would say it more as a support function. You see, like there is uh, uh, like just like I mentioned about this creativity and complexity on this digital solution, that you add more bells and whistles, and then people will start hating it more and more progressively as you put more bells and whistles. Need to keep it simple. Uh, the kind of the similar pattern flows from our organization. There's an optimum size of that organization, right? And everyone needs to follow the same wavelength, right? So let's say you have the petroleum engineer that does the day-to-day optimization stuff and validating the well test, etc. You have the process engineer who is troubleshooting the hydrocyclone of the facility, the mechanical engineer who is troubleshooting the turbine and the other stuff. And then if you get a data scientist there, they will basically try to analyze the past data and trying to build a model based on that, etc. It is not a continuous workflow. It's a workflow that it's more suited as a support function outside of that realm. You see what I mean? It needs to be on the same wavelength for it to work very effectively. So it's kind of an art, and you achieve it the optimal by trial and error. So for this collaborative environment, a group of 7 people, only the key people there, another hub that is focused on a particular discipline, another discipline, but the key core team, it's very few people. Yeah. Yeah, definitely in the asset team, definitely. Having one data scientist would open a lot of doors in the high frequency, this face-to-face continuous operation thing. Not so much. In my opinion, we haven't tried it, but yeah. We had in Denmark, there was an example of the guy that was doing that. He got so excited with operation that he just quit machine learning and he went to work in the platform. So
Wow.
it's a different. It's a better to keep as a support role.
Wow, excellent. Thank you. So I guess the last question is coming from just one second, please. From Daniel Tamunosiki. Apologies if that wasn't pronounced correctly. So with all these in place, will the time given for production be shortened? I guess he's trying to ask about from the time you identify an opportunity to actually get into production. Will that time be shortened?
Yeah, definitely. So that is the value of getting these assignments in place. The ticketing system, how we call it, where you identify an opportunity and you assign it to a certain person. That person, as soon as they get assigned a ticket, they get tracked. So that ensures that the stuff is happening on a timely fashion because everyone can see what everyone is doing. So for sure, there needs to be a reduction in the cycle time for remediation of issues, and also a much faster decision making as a result in the operations domain. Let's say an example. For example, you have the measurement problem, and then the petroleum engineer may find some suspect measurement problem on the water injector. Because the reservoir engineer complained to him that the model are not matching, right? So then that's not enough. If you tell the instrumentation guy, like, hey, I think there's a measurement problem, they will probably not pay attention to you because they're very busy with probably 700 other flow meters across the field, right? So you need to prove it, qualify it by running a surveillance on the meter, running a virtual meter, calculate in a completely alternative calculation and validate and say, like, look, if we have this rate, it cannot possibly be physically true. Please go ahead. this is my proof, move it. Right, so yeah, I hope I made myself clear there.
Yeah, thanks very much, Carlos. While we're talking, another question came in. If you don't mind, we just quickly ask. That's from Kunle Adesoye. Says, thanks, Carlos, for this eye-opening presentation. So how can this optimization technology accommodate new or future surface projects? Take, for example, surface facilities upgrade or expansion.
Oh, this is interesting. This is interesting because you have a network model, and then the network model is used for instantaneous optimization, and as we mentioned, it's also used for short-term production forecast. Right. So the short-term production forecast intention is that you can commit to a certain level of production. So as a short-term production forecast, you also include your facilities that will come online over that short time. Now, we always talk about short-term here, but you can also extend it and make it longer. But in that case, you need to embed more complexity from the reservoir side, reservoir simulation, or etc. And then the one idea, different approaches, but one approach is that this is the same model. The same model that you use for day-to-day optimization is the same model that is used for debottlenecking, future debottlenecking activities and field development plan. Like you have all your future facilities, you just switch them off and run your optimization. And then once you want to run your forecast, then you switch it on with the right schedule. So in the model, it starts running and gives you the forecast. So it can accommodate these future surface projects, etc. Yeah.
Excellent, Carlos. Thank you very much for such a mind-blowing and mind-opening and eyes-opening presentation. And I'm sure everyone has, we've learned so much, even myself personally. I've learned a lot today. So would like to say a very big thank you to you for such an interesting and engaging, exciting session we've just had on a comprehensive framework for production optimization powered by data analytics and artificial intelligence. Hopefully everyone will take on board what we've learned towards achieving the potential for our assets, where we work on. And also would like to thank all the participants today for your time, and because without you, today's webinar would not have actually taken place. So, but before you go, please, we have a couple of few announcements and upcoming activities that will be showing on the screen. First is we have the ambassadors lecturer programs in secondary schools and student chapters ongoing. And also the 2021 annual general meeting is planned for the 31st of July at Eco Hotels and Suites. It's actually going to be hybrid. So that's something to look forward to. It's an award, it's going to include award ceremony, so that's going to be very interesting. Also, we have the scholarship program to support our young professionals that are seeking to advance their postgraduate studies abroad. The scholarship is actually covering IELTS and TOEFL, GRE, and application fees for 2 schools. We have some requirements. So if you or someone meets those requirements, please avail yourself the opportunity to register before 30th of July to take advantage of that opportunity. Please connect with us with SPE Lagos section. Connect with us on LinkedIn, Twitter, Facebook. We have all our social media handles. Please follow us and share as well. For membership, if you're not yet a member or you're yet to renew your membership for the year, kindly contact the email addresses shown above and also the mobile numbers that is shown on the screen. And for SP membership benefits, please visit www.sp.org/members/benefit as shown. Thank you very much again for your time. We really appreciate your time and effort and being here today. Thank you. And I want to believe that the pictures that have been taken, please let's turn our videos so that the pictures can be taken, the snapshots can be taken before we all say, have a wonderful day. Let's say cheers. Cheers.
Cheers.
Cheers. Okay. Thank you very much, everybody. Thank you, and have a wonderful day.
Can you just hold on a bit? Let me just take a few more.
Okay.
Just turn it on down. Say
Okay.
the next 30 seconds. I'll turn it off. Thank you.
Excellent. So let's know when you're done, Odion. Thank you.
Bye. All right, all smiles, everybody. Cheers. Lovely. Cool. I love the smiles. All right, I think we're done. Yeah, over to you, Lanike. Thank you, everybody.
Okay, thanks, Odion. And thanks, everybody, once again. Have a wonderful day, and please stay connected, stay safe. We are SPE.
Thank you very much.
Thank you.
Thank you, Nikki.
Thanks, Thomas. Thanks so much for joining us.
Thank you.
It's well appreciated. Thank you.
Great.
Thank you. Thank you. So hopefully sometimes we'll have more again.
Please invite me.
I will. Definitely we will. We'll be looking forward to that. Thanks so very much. Thank you.
Okay, goodbye.
Goodbye. Bye.
Thank you, Carlos.
Thank you.
Muchas gracias, Carlos.
Gracias.